Corporate Finance Core, Topic 11, Learning Objective number 5. We're going to understand and use a consumption smoothing retirement model, determining optimal savings needs and the probability of retirement shortfalls. So we're going to go to a different file, not your Topic 11 start file, but a file I have here called Topic 11 FinPlan 2 9019.1. So let's look at this model. It kind of follows from the analysis we've done so far. So let's look at some of the assumptions. Remember, the assumptions are in this color here. Current age, you plug in your current age, what age you like to retire, your current income, it could be your individual income or family income, gross, pre-tax. The expected salary increases per year for the rest of your life. Your current portfolio, we'll say you've saved nothing at age 21. You're going to save 15%. There's no company match. Inflation is going to be 2% a year. Some further assumptions. Again, this model is going to try to figure out what's the probability you have enough money for the rest of your life. So I need to figure out how old are you going to live. So I'm going to put in 85 as the life expectancy. And there's a note in there. If you're doing this for 2 people, some data I have for retirees show that if you make it to age 65, one of you is likely to make it to age 91. So what I'm saying is, if you're doing this for 1 person, I would do it at age 85. And if you're doing this for 2 people, I might use 91. And the life expectancy, standard deviation. So if you have 85, you're expected to live to 85 with a standard deviation of 7 years. That's based on some data that was given to me by an actual science person working in insurance. However, if you're looking at 2 people, the standard deviation would be 5. So I generally use 85 and 7 or 91 and 5 if you're going to do this for a couple. And here's some assumptions. I have the Social Security annuity and pension income replacement rate. So let's assume there's no pension, so all this is really Social Security, but you could throw a pension in there also. Let's assume that the Social Security is going to replace 32% of your income, and I've done that based on an algorithm I've written to roughly calculate Social Security. If you want to see that, you can hit Alt F11 and see the function I created, SSA, and you can check out what I did there. But it's just a rough estimation of how much Social Security is going to be. So that's calculated for you. Make an assumption that you're spending 25% in housing before retirement and after retirement. This allows you to downsize if you wanted to. You can say I'm going to save 20 and go down to 20% in retirement. Your pre-tax average tax rate, your pre-retirement average tax rate of 20%, and then in retirement, say it goes down to 15 or even lower. It could go down to 10. What else here? The retirement expense increase. So in retirement, do you expect to spend more, say travel, or more for healthcare? Or you can put a negative 5% in there and say that is going to be I'm going to eat out less, and I'm going to save money on commuting. So I'm going to put 5 there. And then there's my formula. Takes what percentage of your retirement is going to have to be replaced with your portfolio. So it's basically it's 100% minus your Social Security replacement, minus your savings rate, minus any changes in retirement, minus any changes in housing, and plus or minus the last retirement expense. And notice I've used some range names, so if you want to see exactly what's going on, you can see I have range names. All right, so there you go. So I need to replace 63% of my income to smooth consumption. Oh, by the way, this is the basis of this model is consumption smoothing, and what that refers to is the year you retire and earn no income, you want to have the exact same non-housing consumption that you did the year before. So it's going to back into how much you need to withdraw, which is basically this calculation here. This 63% replacement. It's making sure you consume the same amount in non-housing consumption. This model is based on real returns, so to say the nominal returns minus inflation. So that's why stock returns aren't around 7 or 7.5. They're 5 and so on. So here are my correlations that I've received based on some data I collected over about 10 years. And here's the standard deviations. US stocks 17.5%, foreign stocks 20%, bonds 4.7, money market 165. And here are some, again, and if I combine my covariance and my correlations, my correlations and my standard deviations, I get these covariance numbers I talked about in that earlier topic. All that information allows me to say when I'm age 22, assuming I'm in a target date fund, I'm going to have an expected real return of 504, which is probably more like 704 if you're looking at nominal returns, and a standard deviation of 6.5. There's my income growing each year by that 3% growth rate. Here's my savings, which is going to be the savings rate plus contributions. Here's my housing expense. Here's my non-housing consumption. So it's my income minus my personal contribution. Actually, that does not include the company match, minus my housing. So that's how much I'm living on. Family income minus taxes, minus contributions, minus housing. And here's my portfolio value. Starts off at 0, grows at 5.04%, plus the new contributions. And it looks like my static portfolio will last until I am, let's see when it runs out of money. Well, actually, here's age 65. Then I jump over to here. These are retirement years. And here's where it starts going down. And it looks like this portfolio will last until you are aged 109. So you run out of money in 109 or 110. And so here's my static portfolio model. It looks like you have plenty of money. It lasts till you're 109 years old, and you're expected to live till 85. So you have 24 extra years. You have negative shortfall years. So you have plenty of money. This also tracks when you retired. You had 13.6 wealth to income ratio. So it's my portfolio value at age 65 divided by my income in that final year. I'm going to expect to retire on a portfolio in nominal terms of $2.7 million. So this is the static model. However, the next column here in M is the random model. So notice I have to replace the expected return with a random return. So what I do is notice I have the norm S inverse ran there. There's my random return, 1 plus the expected return plus the random number times the standard deviation. So it's doing the same formula as the static portfolio, except it's using a random return. And then every time I would hit F9, I would get a new set of portfolio values. And again, here's my macro simulation. Here's my my simulated values. So we can come down here, and every time I hit F9, let's look at retirement years. Every time I hit F9, what you might see eventually is you get some situations where you have some negative years or portfolio running out before you die. Let's come over here. Don't worry about column N. If you know the at-risk model, that uses at-risk, but we're not using that. Here's some data I've collected from every time I hit F9. Every time I hit F9, I get a new portfolio value. So notice this cell in P8. So every time I have 9, that's a random portfolio value. So this random markets gave me 3 million, 1.4 million, 2.5 million, 2.2 million, and so on. Now again, if I did that 5,000 times, on average, I'm going to wind up with $2.7 million, which is the static value. Now, here's my random wealth to income ratio. Sometimes I got 5 times income, sometimes I got 20 times income. So that's interesting. Portfolio death. So this tells me every time I have 9, it tells me what age my portfolio ran out of money. Now here's my random walk model of death. So it's your life expectancy, 85 years in this case, plus the norm S inverse ran, that random number, times the standard deviation of lifespan. So every time I hit F9, that's the age of my death. So I died at 83, 81, 94, 93, 89, 87, and so on. Now for planning purposes, what you really care about is when your money dies before you do. So let's look at this random situation here. In this state of the world, the state of the portfolio returns over the 50 years of my life, remaining life, or 70 years of my remaining life. In this one, my money lasts till I was 104, but I died at 90. So that's okay. I had a long life. My money lasted a long time. Here, my money lasted till I was 94, and I died at 84. So I had a short life, but I had enough money. Oh, here's a bad situation. Well, I don't know what you call it. I lived till 92, but my money ran out at 86, so I had 6 years I ran out of money. So what would be interesting is to do this F9 5,000 times and record 5,000 portfolio values. On average, it should be $2.7 million, but I also can look at, say, the 5% worst and best case. And I calculate maybe the probability that I run out of money. What percentage of the time is my portfolio dying before I do? So how you do that is you click on Run Simulation. What it's actually running, I'll hit Alt F11. It's running this little macro that does the recalc, hits the F9 for you, or turns on. So it turns off turns off automatic recalc and does the F9 for you down here. And then this cell 16.4, it's the 16th row, 14th column. It's going to do 5,000 minus I, and it's going to do a loop. It's going to do a countdown of 5,000 F9s. And then it's just going to record your portfolio value, when your portfolio died, when you died, and it's going to put them in this cell the first time you hit F9, and then, this row, and then the next row, and then the next row. And then we calculate some statistics over here. So I'm going to run this. Now, it looks like my portfolio is a little timed out, so I'm going to hit escape a couple times. Hit end. And based on that information, so these are the 5,000 iterations. And here's what you find out. On average, you will get $2.7 million, exactly the static model. On average, you will retire based on these assumptions with a wealth-to-income ratio of 13. On average, your money will last 109 years. On average, you will last 85 years. However, only about 75% of the time will you have enough money. In other words, this strategy, even though it looks really good, there's still a 25% chance you run out of money, because it's looking at all these 5,000 situations here and counting what percent of the time did your portfolio die before you did. And it also does some interesting things. It does the 5% smallest and largest portfolio value. So 5% of the time you retire with a portfolio of less than $1 million. 5% of the time you retire with a portfolio of $5.8 million or more. So this is the idea of a probabilistic or stochastic model that allows you to look at not just what's expected to happen, but what could happen. And then you can change some assumptions and see what happens to that probability. 75% is almost as good as it gets. This is a pretty good saving, pretty good plan, saving 50% of your income all your life and invest it in a target date fund. So this is the model. This is how you use it, and it gives me similar results to when I get professionally done models through my retirement managers. So that is a determinant or a stochastic consumption smoothing retirement model, which is the basis of most models that you'll get if you get a personal financial plan.